Welcome back. Let's just go ahead and continue. So that's a very simple example, but actually it's much more general than that because you can have much more complex queries with different transformations, with more lines of code and so on that you put in your Jupyter notebook. So let's go through the restaurant menu, right? It's exactly like ordering your starters and entrees and desserts and so on. Okay. So a transformation is the generic name that is given to a logical function that turns an RDD into another RDD, or that turns several RDDs into another RDD. It's a generalization of the concept of map and of reduce, but with anything, right? So now I have plenty of visuals like this, where I have a transformation at the top and the resulting transformation at the bottom. So of course, now this is just a generic slide, so it doesn't show anything, but let's look at one. So on the menu, we have the filter transformation. The filter transformation basically filters a subset of an RDD, and that subset is the output RDD. How do you specify which subset you want? When you need to supply a function, it's this lambda that you saw in the code. You need to supply a function that takes a value from your collection, and it says yes or no. Yes, I keep it. No, I don't keep it, right? So it's a yes-no function. And what happens is that Spark is going to call that function on every single value in the input RDD. And if it's yes, then it keeps the value. And if it's no, it doesn't keep the value, right? Now, it's of course going to be done in parallel, but that I'll come back later, right? But logically, this is what happens. You have an RDD and you get a subset of the RDD. Who is with me? Right? That's a simple one, right? Very visual. So it's just a filter. Here's another one. It's called map. Map basically turns an RDD into another RDD. It associates every value in the input RDD with one value in the output RDD. So you have here an example with the row that this value got turned into this one, this into this one, this into this one. It's a one-to-one mapping, right? So in that case, all my function does is that it paints the value orange, right? So that's what the function does. And again, we can apply it in parallel, but that will come back later. This is called the map transformation. Who is with me? This one is easy too. Okay. This here is the flat map transformation. This one you already saw in the example. Flat map takes a value from the input RDD and turns it into 0, 1, or more output values, right? So for example, on the drawing, you have this specific input value right here that is mapped onto these 4 right here. But it's a flat map. So it means that once we've done that for every value here, we flatten everything again. It means we forget which values came from where, right? Once we have done that, we no longer know that these 4 came from the same place. This is why it's a flat map. Okay? Now, let me ask you a quick question. If you want to implement MapReduce, the map phase, is this the equivalent or is this the equivalent of MapReduce? So let's do a poll. You can answer either this or this, which is the equivalent of the MapReduce mapping. Who thinks it's this one? Okay. Who thinks it's this one? The other one? We have more hands. In fact, you're right. You shouldn't trust the names. The actual equivalent of the map part of MapReduce is flat map. Do you remember in MapReduce, the map function takes a key value and returns 0, 1, or more key values, right? And then we flatten, we didn't say it, but we actually flattened the intermediates, the set of intermediate key values is all flattened. So flat map is the way to go if you want to simulate MapReduce or execute something like MapReduce on top of Spark. You should use the flat map transformation for your mapping phase, okay? And even though it's called map, this one is different because it forces you to map each value to one value. Okay. Here's another one. This one is called distinct. What distinct does is it eliminates duplicates. That's what it does. Yes, we have a question. Go ahead.
Thank you. In flat map, is the mapping always to the same cardinality of dimension? So is it always 1 to, for example, 4 or 3 for one specific version of flat map, or
No
does it depend? So each
can be different every time. Maybe you're going to map the first value to 2 values,
okay,
the second one to none at all, the third one to 1, the fourth one to 5, and so on and so on. There is absolutely nothing that forces you to always output the same number of values here, but it's the same as in MapReduce, right? It's exactly the same in MapReduce. You also don't have any constraints that it must be exactly the same number every time. Think of the example with splitting the string, right? It might be that you have a string that has 2 spaces, in which case you output 3 substrings. It might be that your string has no space at all, then you output exactly 1 string, and so on and so on. Right? So there is absolutely no constraint. In other words, it's dynamic, the number of keys. And in fact, you don't even know it in advance. You have a function, and that depends on the value you're processing. All right. I'm removing the noise again. Distinct. So distinct eliminates duplicates. So I use colors in there, right? Because it's more visual. So you can see that I have multiple times the same green. I have blue 3 times. So what I do is that I had it 3 times, now just once. I just eliminate the duplicates, right? That's what it does. Just a remark, en passant, notice that it feels a bit spaghetti-y, right? Compared to this or this, right? There's a bit of spaghetti here. I'll come back to that, right? There is, in fact, it actually means something on the physical level, whether there is a spaghetti or not. All right, here's another one, another transformation. This one is called sample. It's a bit like filter in the sense that it outputs a subset of the RDD, except that there is no yes-no function, or more exactly, the yes-no function is random. It basically rolls the die every time to see whether you keep it or not. And you can say how much you want to keep. You can say, for example, I want 50% or 25%. You specify the fraction that you keep, but it's all based on random choices. Now, you know, random choices with computers is not exactly random. It's actually pseudo-random. We simulate randomness. And what you actually do is that you have what's called a seed, right? And a seed is some value that you feed in there, then it looks random, right? So you can also control that, but that's basically the idea of randomly selecting that and that many % of your data set. Can be useful also in machine learning, right? You have a huge data set, you want to train on 10%, then you just say, sample 10% of my data, and it's going to randomly pick 10% of the values. With me, right? That's also a simple one. Okay, so these all imply 1 RDD to 1 RDD. What happens with 2 RDDs to 1 RDD, right? So here's one that's called union. Union takes 2 RDDs and it's concatenating them, right? Which is an opportunity for me to say, not remind because I might not have told you that, these collections of key values, these collections of values, the RDDs, have an order in Spark. The order actually is important. So it's not a set, it's a list. So technically, when you use words like union, intersection, and so on, it's kind of a bit of an abuse of language, right? Because technically it's a list and there is an order. So union, in fact, is a concatenation of lists, right? If you're a mathematician, think of a monoid. That's what it would be called. So we concatenate the 2 RDDs, and now we have a new RDD, and all the first values come from the first RDD and the other values from the second one. Who is with me? All right. Is there spaghetti in there? There's no spaghetti, right? That's also something to keep in mind for later. Okay. Now there is spaghetti. This is real spaghetti right here. So we have 2 RDDs. What do we do here? We compute the intersection. It means that I'm looking for all the values that appear on the left and on the right, right? just once. For example, there's blue on both sides, there's green on both sides, there's orange on both sides, and there's purple on both sides. So I would put blue, green, orange, and purple. Yellow, no, because it's only on the right. Black, it's only on the left. Red, it's only on the left, and so on and so on. So this is the intersection. Again, spaghetti all over the place on that one. Okay. Okay. Yet another one, subtract. Here, you basically output all the values from the left RDD, except if they are on the right. That's called a subtraction. Right? Who's with me? And here, there is no spaghetti on the left, but there might be a bit of spaghetti on the right. You see what I mean? So what you output is basically nicely parallel compared to the first RDD, but you still need a bit of spaghetti to compare with all of the values on the right. Okay? So let's call it half spaghetti, this one. Is there a question? Oh, that's a very good question. No, without replacements. I didn't say it explicitly. So you will not output twice the same value. The way to see it is that when you have a sample with replacements, what you do is that you pick a value at random, and then you pick another one at random again from the whole system, and then you pick another one at random. But this is not, that you cannot parallelize. Well, you could parallelize if you're a bit smart, but the way this is executed is not that you pick values at random repeatedly. What you do here is that you pick the values one by one and then answer yes, no. So this is why it's without replacements. Does it make sense? Yeah, all right. But that's a very good question, very good critical thinking. Okay. All right, so this is the subtraction. Here's another one. That's the Cartesian product. The Cartesian product also takes two RDDs, but except that the two RDDs now I didn't display them in the same way. I displayed one on the columns and one on the rows. So the Cartesian product basically looks for all the combinations of values with one value from the left, one value from the right, and it outputs pairs of values, right? So if you have 3 values on the first RDD and 5 on the other, then you have 15 values in the output RDD, right? It's the product of the cardinalities. For whom is that clear? Who sees that you can crash a cluster with that? Imagine there's a billion values on the left and a billion values on the right. You end up with, if I'm correct, a quintillion values in total. You can crash the whole cluster. In fact, this thing is so scary and dangerous that by default, Spark will not even let you do it. You have some global parameter that you can set to say enable Cartesian product, but you need to explicitly do it. If you don't, you will not be allowed to do that. What it means is you need to be mindful of what you're doing. If you ever do a Cartesian product, think twice. Are you sure that your RDDs are small enough that it's not going to crash your cluster? Okay, for who is that clear? All right. Which is why in practice, we don't just use a Cartesian product, we also filter. That's technically a join, right? But I'll come back to the notion of joining. Okay. Okay, these were transformations. Transformations just turn an RDD into an RDD. But you remember that lazy evaluation, if all you do is transformations, then nothing is actually going to happen, right? Because things are only actually happening the moment you trigger an action. So let's look at the action. The action is really at the end, the one that produces some effect. Here's an action called collect. As its name indicates, it collects the values in an RDD. Now, from a mathematical perspective, it's just the identity function. You have a list of values and you have that same list of values as the output. So why do we actually call it something, right? If it's just doing nothing mathematically. It's because physically it's not doing nothing. Physically, what happens is that collect downloads all the values to your machine. This is what collect does. So you have your values, the RDD on the top, that's an RDD, it's all over the cluster. At the bottom, that's a local Python list on your machine, in your memory of your laptop right here. So what this does is really download from all the machines to your local machine. Again, be careful. You need to be sure that it fits, because that can crash your laptop, right? If you have 1,000 values, that's going to be okay. 1,000,000 values is going to be okay. 1,000,000,000 values, 1,000,000,000,000 values, that's going to crash your laptop. So you always need to keep in mind to understand what you are doing, to know if that's a good idea or not a good idea, right? So this is one thing you can do. By the way, there's also alternative to collects that don't collect it to your machine, but that write it to HDFS, right? You can also do that, and that you can do even with 1,000,000,000 values. It's just going to write the files in parallel, just like the output of MapReduce. So you can also write to HDFS or S3 or whatever file system you want. But collect, that will download it to your machine in the memory as a Python list, right? Count, this one you can do with confidence, works all the time. It's not going to crash anything. Count just spits an integer that is the total number of values in your RDD. This is highly parallelizable. In fact, as you can imagine, all the nodes in the cluster will count the number of values they have locally. And then you ship the counts and sum over them, right? So this is very efficient to compute. And then you hold a simple integer on your laptop after you've done that. That's also an action, right? It triggers the whole computations that might have been from transformations before. Then you have count by value. Count by value is also an action. It also downloads to your machine a dictionary. It's a Python dict. It's basically mapping every unique value to the number of occurrences in the RDD. For example, if you have the RDD with the colored squares on the top, what you get is a Python dict with 3 keys, blue, yellow, and green. And the value associated with blue is 12, with yellow is 4, and with green is 6, right? So this is a Python dict that is obtained by counting the number of occurrences. Again, be careful, because if you have 1,000,000,000 values in your RDD and they're all distinct, or there's not a lot of repetition, that's going to crash your laptop as well. So in order to do that, you need to know that the number of unique values is reasonable and fits on your laptop. For whom is that here? All right. Here's another one. This is not risky at all. It's called take. Take just picks the first n values of your RDD. So take 4 takes the first 4 values of your RDD. Okay, it's like a SQL limit, right? So you take the first 4. And the other one is called top. It takes the last 4. Why is it called top? Because there is this idea that whatever comes last is kind of the top of the RDD and the bottom on the other side, right? So this is why it's called top. So take here for the first and here the last. For whom is that clear? Okay. Then we have take sample. It's a little bit like the sample transformation, but again, it's an action. The sample transformation turns an RDD into another RDD. Here, you don't turn an RDD into an RDD, you turn an RDD into a Python list locally on your machine if you use Python. For whom is that clear? Right? So you take a sample, but you download it all to your laptop, these samples, to your laptop or to whatever machine you're using. Then there is another action called reduce. Reduce is basically aggregating the values in some way. For example, that might be integers, and you use the addition or the multiplication or min or max or whatever you want, right? So that's called reduce. So in that case, you would compute the sum of all the integers. Okay? For whom does that make sense? Right? It's easy, right? It's a walk in the park. We're just going through all of them, and I'm just showing to you what they do. Okay, so now we've looked at transformations, we've looked at actions. For generic RDDs, it can be RDDs of anything. So I told you that Spark is more generic than MapReduce because it doesn't have to be key-value pairs, but it can be key-value pairs. And in fact, because it can be an RDD of key-value pairs, Spark has specific transformations and actions that apply to RDDs of key-value pairs, right? So let's go through them. So now I have an RDD of key-value pair. It's a special case of RDD. So I put the keys in blue and the values in gray. So there is a transformation that turns an RDD of key values into an RDD of keys, right? But technically the keys are no longer keys at the bottom, but it basically takes all the keys and gives them to you as an RDD. For whom is that clear? That's easy. Well, this one should be easy too. That's values. So this one returns all of the values and drops the keys. Okay. Then there is reduce by key. Reduce by key is going to group the key values that have the same key, and it's going to invoke some reduce function, in that case addition, but it can be anything else you want, min, max, and so on, and aggregates. So in fact, reduce by key is the reduce equivalent of MapReduce. So flat map would be the map equivalent, and reduce by key would be the reduce equivalent. Who sees that? That this is the same as the reduce part of MapReduce? Who doesn't see it yet? Okay, so we group all of the key values that have the same key. That's what we do in the shuffling on MapReduce, and then we aggregate the values with some function that would be the equivalent of the reduce function in MapReduce. Okay, then we have group by key. Group by key is almost the same, but it doesn't aggregate. So group by key means you kind of do the reduce, but instead of aggregating, you keep all the values. So what it does is that it also outputs key values, but in the output, the values are actually the lists of every value that was in there. So that's a list of 4 values, this one, this one, this one, this one. This is the list of the 3 values here. So group by key. Okay, who understands this one? So it outputs an RDD of key values, but now the values of the output are Python lists, right? Associated with a key and inside an RDD. Then we have sort, because I told you it can be ordered. So you can sort an RDD. You provide a sorting function that says what it means to be greater or smaller or equal to anything, right? And then you sort. In that case, I sorted them, the colors, nicely by wavelength, by increasing wavelength. Yeah. Okay. So you can sort integers, you can sort strings nicely. Okay. By the way, you could kind of do that with MapReduce, but it's a bit tricky. With Sparks, it's much easier to actually sort your key values. Then we have map values. What does the map value transformation do? It basically maps key values to key values, but it doesn't modify the keys. All it does is map a value to another value, keeping the same key. For whom is that clear? You take the key values, you keep the key the same, you just modify the value with the map function. Who understands? Okay, awesome. So map values. Then you have join. Join is a bit like the relational join. It means that you try to put together the key values that have the same key on both sides. So in that case, it's really just like when you do it on 2 relational tables, right? You try to match the records that correspond to records. So in that case, you have, for example, this key and this key are the same. So you join them together, and what you have here is the key that was the same, then the value from the left and the value from the right. Imagine that this is a record from a relational table. This is a record from a relational table. This is the attribute to join on, and then you have the larger, wider table as an output that joins the 2 records here. Then you have, in the case of blue, you have 2 blue and 1 blue that's matched to 2 records or 2 values here, and then the green matched with the green. So this is what a join does. For whom is that here? Okay. So it outputs the keys that are on both sides together with the value from the left and the value on the right. It's a tuple in Python. The value from the left and the right, you would put it in a tuple. Okay. Then you have subtract by key. Subtract by key outputs all the value from the left RDD. But if a key appears on the right, then it drops it, right? It's a little bit like a subtract, but working on the keys. So in that case, we dropped the blue and the orange keys because they appear on the right, but the brown key didn't, so we keep it. Who is with me? Okay. Count by key. Well, it's very similar to count by value, but this one is an action also, but it counts the keys instead of the individual values, right? So blue, 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 blue 6 times, green once, yellow 4 times, right? So count by key. Who is with me on that? Okay, it's an action. That was transformations here. Now it's an action. So that's actually downloading that as a Python dict to your laptop. Then you have lookup. Lookup is a nice one. That's also an action. Lookup returns the values that are associated with a specific key. So you might have, oh, there's a question over there. I hope you haven't been waiting for a long time. I just saw it now. Oh, sorry, almost. let me increase the volume. There you go.
Just quickly, in the subtract by key transformation, will the keys on the left, if there's if there's multiple of the same key on the left, but they're not present on the right, will they also be kind of joined like in the join transformation, like next to each other or not?
I think they wouldn't. I think if you have, let's say, 3 keys that are the same on the left, you would still output the 3 keys. All it does is remove something, but it would preserve, because the key values might be different, right? So I don't think it merges anything.
Thank you.
We could check actually just to be sure if you can take a note that we can confirm, and we'll tell you if I'm wrong, but I think it doesn't merge anything. It really preserves.
Thank you.
Thank you. You can throw that back. Wow. You can go to the Olympic Games. You're really good at that. Okay. So lookup, just if you have trillions of key values and you look for a specific key, the orange key, then lookup will return the value or the values that are associated with that key. Right. By the way, I didn't say it explicitly, but the keys can repeat. There is no constraint here that you cannot have repeating keys. In JSON, you cannot. In a JSON object, you cannot. In XML attributes, you cannot. But here, there's no problem at all. You can have absolutely repeating keys. And in MapReduce as well, by the way. Okay. Okay, that was the logical layer. So I basically walked you through the menu. Now you can do whatever you want. When you write a Spark program or a PySpark program, typically you have a specific problem in mind. You have downloaded a data set from the internet. You have put it in the data lake in S3 or HDFS. And now you sit in front of your Jupyter notebook trying to write queries to transform the data. So typically what you do is that you have the documentation open on a screen maybe, or you have a book, a reference book, and you just look in the menu for the transformations that you need, and you assemble that like a Lego game into a Spark job, right? Who is with me? Okay, that was the logical part, and you'll have an opportunity to exercise that. At the exam, you will have PySpark. In fact, now we managed to find a way to download the entire documentation of Spark and have it on the exam computer. How cool is that? So you're going to have normally the whole PySpark documentation on your exam computer available for you. All right. And you can thank the students of the last semester for that. They pushed for it, and so we worked hard to make it work. Okay, which brings us to the physical layer. That's the part the user shouldn't care about. But still, it's interesting to understand how it's executed. And now you will see that actually knowing how MapReduce works is very useful to understand how Spark works. Do you remember how, when I showed you the transformation, I said, okay, this one is not spaghetti and this one is spaghetti, right? So let's start with the transformations that are not spaghetti. Well, technically, the word for that is narrow dependency. It means that the values in the output depend on only very few values in the input. In that case, it's a map. So every value depends on one value in the output. Who feels it's parallelizable? It is, right? Parallelizable. Let's do it. Let's split it into tasks, right? Now we have tasks. So now you kind of probably start getting the intuition of what's going on, right? We are going to parallelize like this. And by default, the input, we can read an RDD from HDFS, right, as a data set, for example, from HDFS. And guess what? Roughly speaking, every HDFS block gives you one task. Exactly the same as in MapReduce. But roughly speaking, because again, there's this bit versus value separation thing, so you might have a spillover on the next block for a few bits, right? Okay, so what it means then is that when you have a transformation that turns an RDD into another RDD, or at least that's how it feels from your Jupyter notebook, right? You have an RDD and you invoke a transformation. But what actually is happening behind the scenes is that you have a data center. And what's happening is that you might have 4 machines, and every machine is working on a task, right? So now this is the case where there are as many tasks as slots, but you know that in practice, this is not how it works. You have more tasks, and when a slot is finished, then they get the next task, right? So basically, it looks more like this, right? In that case, you have 11 tasks and 4 slots, right? So it's roughly 3 times as many tasks as slots, which is kind of nice. Spark calls these executors, right? So it's the containers from Yarn. So it calls them executors. So in that case, if I assume 1 slot for every executor, I start with 4 tasks, and then this one is finished, takes task 5, and this one is finished, takes task 6, and so on. And then some of them are faster and take more tasks, and some of them are slower and take less tasks. This is what I re-explained in the first hour, right? Who understands that? Right. So technically, you split your RDD into partitions. That gives you the tasks, and then you spread over the tasks on these slots, and the slots just consume the tasks as long as there remain tasks, always more tasks than slots. Now, to be more exact, the way that it works in Spark is that you might have multiple cores in the same container. Remember, in Yarn, you can have a container with 2 cores and that much memory. So these are, in fact, the slots. The slots corresponds to CPU cores. But what happens, what we call an executor, is that it's different slots that share the same memory. They have the memory in common, right? That gives you a bit of flexibility. For the case that, imagine that this slot is using more memory than that one, it's a bit more flexible. But between executor, it's rigid. So if this is using more and less here, then there is no sharing, right? So then you're just wasting resources here and not there. So having shared memory allows you to have a bit of flexibility in the usage of the memory. For whom is that clear? Right? So the executors are the Yarn containers, and in the executors, you have several cores, and every core gives you 1 slot. And 1 slot executes the tasks one after the other sequentially. Okay. Let's continue then. This was for just 1 single transformation, like the map phase of MapReduce, technically. This is exactly like the map phase of MapReduce. So what happens if we have several transformations? Let's assume these transformations are not spaghetti. These are all narrow dependency transformations, like filter, like flat map, like map, like sample, like this kind of transformations. So they are not spaghetti. So you might think, okay, it's 3 transformations here. So why don't we just treat it as a map, shuffle, map, right? We could kind of generalize MapReduce in this way. So I could have machines that execute the first transformation, then other machines that execute the second transformation, and then other machines that execute the third transformation. And in the middle, we might shuffle again. Do we really need to shuffle? Because if you look at this, it kind of feels like the shuffle is not really required, right? The shuffle is kind of useless in here. It's just a waste of network. Do you see that we can do better than that, more efficient than that? Who sees that? How can we do it better than that, more efficient? Does anybody see it? Who sees that we are wasting machines and we are wasting network bandwidth in here when we do that? Let me explain the idea. What do we want logically? Logically, I have this input RDD, and there's 3 transformations, and I get this output RDD, right? Anything that happens in the middle, I'm free to do it in whatever way I want. All I want is the correct RDD at the end. Do you see that if you follow the edges here, to compute that value, it's basically a chain of function calls from here to here, but without any spaghetti. Do you see that could be done on the same machine? And that too, and that too. So in fact, you can do it that way. It's completely equivalent, but now it's the same machine for the 3 transformation for a specific subset of the input, and then another machine for all the transformation for another set of the input and so on. So now we basically share the slot across the transformations. For whom is that clear? Okay, this is the same thing, but this is more efficient. So what happens is that when you have a sequence of transformation and these transformations are not spaghetti, then we can squeeze them together onto the same slots. This is the same tasks here. There's 1 task, 2 tasks, 3 tasks, 4 tasks in total. But within these tasks, we change the function call that correspond to the transformation, but it's all local on a single value at a time. Is there a question? Do you mean here? So yes, that's highly inefficient. This is super inefficient. That would be the naive way of doing that. But the way you do it is like this. And once you do it like this, that's called the stage. So it's basically a group of transformations that are all narrow dependent, no spaghetti. In fact, what you do is this. You basically now have exactly the same idea of tasks that are spread all over the machines. But do you see that the difference is that now on that slide, we have 2 transformations instead of 1 transformation. That was if I rewind a little bit, that was with 1 transformation. And that is the same thing, but now we squeezed 2 transformations into the game, but we still have the tasks organized in this way. There is still a follow-up on the question? Oh yes, but then you just pick tasks. It's exactly the same idea as in MapReduce. You just keep picking tasks, and at some point you're done with the task. But then it's no different than MapReduce, right? Once you run out of tasks, then yes, you start being idle at that point, right? But since you arrange to have more tasks than slots, then that kind of evens it out. Okay, the last slide explains. Very good. Okay, so all of that you can control. In fact, when you submit on the command line, so that's outside of the Jupyter notebook, you can say, I want 42 executors, I want 2 cores on every executor, I want 5 gigabytes of memory for every executor. All of that you can configure, right? But typically for the exam, you don't need to do that. This is already pre-configured and automatic. But just to say that you could, if you wanted to, you could control. Now, that only works for the narrow dependencies. If you have spaghetti in the transformation, then that doesn't work anymore. Because what happens when you have spaghetti, you need to what do you need to do if there's spaghetti? Start with an S. Shuffle, yes, exactly. You need to shuffle. As soon as you have spaghetti in the transformation, you need to shuffle. So it means that the transformations that don't have spaghetti, you squeeze them together as the same tasks. And if you have spaghetti, you just shuffle. So what typically happens is that every transformation that has spaghetti triggers a shuffle, 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 shuffle. So typically the way a generic Spark jobs works is that you have stages separated by shuffling. And of course, it's like a game. You try to minimize the shuffling. You try to write your code in such a way that there's as little shuffling as possible, because shuffling is what actually takes time. For whom does that make sense? Right? That's the generic way a MapReduce job looks like, even more generic if you have joins and that kind of things. And the stages are sequential. You execute stage 1 and that's stage 2, and that stage 1 is going to shuffle from 2 places. It means it's downloading from the left and downloading from the right, but it lands then in the same bucket, what has the same key, and so on and so on. So this is the most generic you actually get. So again, you need to think of it this way. You have transformations. If they are narrow dependency transformations, no spaghetti, you can squeeze them into what's called a stage, and the stages are separated by shuffling. The stages are split horizontally. This is the tasks, right? In order to execute a stage, you split it into tasks, more tasks than slots, and then you do it over all the data center. And a sequence of stages, so stage shuffle, stage shuffle, stage shuffle, is a job. For whom is that clear? All right, so it's a generalization of MapReduce, because now we just don't have map shuffle reduce. We can have as many stages as we want with as many shufflings as we want in our Spark job. So I'm going to leave it here for today. I'm going to talk next week a bit about performance and about data frames, using data frames and Spark SQL, which is even better than PySpark, as we will see. And you will see why SQL was actually useful to learn or to brush up. You probably already have an intuition of that, right? Because if you look at sorting and grouping and filtering, it kind of smells like SQL already. Okay, so just before you go, I would like to check that you actually understood. Where is it? There you go. Just checking that you're with me. Okay, that looks better than last week. So it was worth the effort of taking the time. So next week I'll finish that. Then I'll talk about performance at large scales, and we might start document stores. We are almost there technically, right? Document stores, JSONic for querying trees, and that will be the end of the semester. Thank you very much. I hope you enjoyed it. There is no exercise week this week because it's the 1st of May. So we even if you're on Friday, we basically drop everything this week. I think there's no quiz, right? There's no quiz at all this week. Yes, we extended the deadline, the TA team extended the deadline by 1 week. So use that in order to breathe a bit, read the textbook and practice. And if you have questions, then collect them. Don't hesitate to interact on Moodle. Thank you very much, everybody. And see you next week then for the next lecture. Thank you very much.